comes in here likewise, and consumer consume it and sending a signal. Okay, and then this thread preceded, and this signal goes to this thread, so spinning. So no one progress. Consumer a producer holding a lock here, and the other consumer also holding a this while statement, so no one make a progress, which violate Leibniz guarantee. Okay, the correct implementation is changing. So the root cause is that the signal is delivered to this one, so the signal is delivered to this way, having a direction. So make direction using different conditional variable. That is correct implementation for bounded buffer, right? So that was the. So I want to make correct that, to interpret these two implementation, let's talk about safety and liveness. Okay, so that was the correction I want to make before moving to the persistence storage section. All right, so let's moving on. So we are now we discuss virtualization. So the process abstraction, thread abstraction, scheduling, and virtual memory, virtualized system. And then the next we are working on concurrency. The thread is as an execution unit, and we discuss several concurrency problems. So in terms of operating system designer, important thing is how to implementing a lock. So we discuss several different implementation of lock using different atomic instructions, and then we also talk about different synchronization primitives like conditional variable and semaphore. Okay, that was the concurrency part, and now we are moving to the final section of the operating system, which is persistence. I posted the storage part, right? So storage online lecture for storage part. Again, I'm sorry for upload the storage lecture late. But again, this file system lecture has something to do with storage lecture, but no, you can understand. You could understand this file system lecture without having a deep knowledge about storage section, right? So persistence lecture, you can talking about storage system, which is hard disk and SSD. Some row level architecture hardware features to support I/O systems, right? And then we are talking about file system, general design aspect, and implementation. One thing you have to keep in mind is that file system is pretty detailed. So you may heard about the word, devil is hidden in detail. That is what exactly, that kind of, saying is what exactly describe of file system. The file system has numerous detail. So even if we know some kind of design concept, correct implementation is super challenging. We will discuss this implementation aspect of file system. And then we will talk about some example of file system is called fast file system, FFS, as an example. And then we will talk about crash consistency. So this full lecture, key flow of this persistence lecture, and this is online video. Video lecture. I recorded it and uploaded it in the Piazza. Okay, so we will skip this part and start talking about file system. Okay, let's begin. So the first part is about talk about file system high level design. So file system layers, this is kind of, spoiler alert. So what we are talking about, the entire stack, is file system, which looks like this layer. This part we are talking about design. So I will using some design jargons and design terms to describe things. When you are drawing some kind of complex software stack, this is box, right? So boxes. Okay, so but these boxes are stacked in. Okay, so what is it? Talking about layer. Stacked box. Okay, so layer means that there is some kind of information comes from the upward and going downward to execute. So upper layer sending API to lower layer, and after lower layer get event, this event eventually delivered to upper layer. So file system has these several different layers, meaning that so data structure used in the device disk control interrupt controller and device driver and general block layer, and file system each one is isolated, meaning that there's no direct reference to this one. This information is translated to lower layer and information is transferred to lower layer. We learn this kind of concept. We learn some term to describe this kind of design. What was that? Pretty long, right? So we may forget that. So at least you are actually taking some, operating systems course related to design. Okay. So this type of design is called layers of abstraction. Okay. So these are each abstraction layer. So these details of general block device operation, these details of the device driver are never exposed to up layer. So complexity we handled within the same layer. So we can say this is abstraction. And abstraction is stacked here. So you can say, well, layer of abstraction. So in this regard, operating systems consist of layers of abstraction. And we're talking about different layer of abstraction in memory system and file system, memory systems and scheduler. So scheduler, for example, in application, this is kind of scheduler kernel, scheduler that goes to CPU. Rather simple, right? So directly there's no kind of this device driver like things in the scheduler. However, file systems typically complicated because there are a bunch of different devices exist. So to support different storage medium, hard disk or SSD, we need some layer in device driver. When you're looking at this storage lecture, I describe kind of this, the role of device driver, which hide details of hard disk and SSD and providing general interface to general block layer. And general block layer is nothing but like this block read and write operation. So this kind of device is block device. So block device is represented as general block layer. And then the file system using this general block layer interface to sending data. So there are tons of different file systems. You know how many file systems exist nowadays? More than 900 file systems. They are using this general block layer. Okay, so they don't care about this internal details, and they implement the high-level file system functionality because of this benefit of layer of abstraction. Okay, we already discussed that, right? So we are talking about this file system. So in the file system, again, this general block layer exposes storage as this logical view. So this is called kind of LBA. So all the storage devices as logical array of file. Okay, so there are block interface abstraction. So you can think about chunk. This is a sector in hard disk, HDD, page in SSD. In case of page, the size is 4 kilobytes. Anyway, So some fixed size of chunk are array. So this is logical view. Therefore, using in this general block layer interface, it identify that. So they here are kind of three operation. Identify how many kind of blocks I have. The file system needs to know maximum block size. Return no, so get the size of block. And then for read operation, I want to write my data in block number, sector number, and how many sectors my data can contain, and the location of my data. So buffer, applications, application, buffer are eventually copying into this logical location, where this start sector and side of sector are specified. Okay, so that is what kind of file system does, copying user buffer to specific file location. So how to manage, how to allocate it is kind of an internal implementation of file system. So that is kind of the first things you have to know for when you design a file system. Okay, logical view, so interface like this one. And this is what you have to do, copying the buffer into a logical view of files, logical view of storage devices. So the file system and memory system resembles a lot. So most common features, kind of sharing feature is this level of indirection. Okay, so level of indirection, just we may forget that, so I just kind of recall. We already discussed this one. In virtual address space, each thread has own address space. So each address space consists of this stack data code heap, and different process having a different address space. So this space does it isolate each other and own view of logical space. And this space are mapping into physical memory. Some mechanism is required. What was that? Okay, again, what mechanism allows this level perform this level of indirect operation? What was that? In memory system? Come on, what was that? What? Well, address translation mechanism. Specifically, what? What address translation mechanism I'm talking about? What? Okay. Paging. Page tape. And the other one? The other one. TLB is kind of hardware that actually improve performance of this translation. What other mechanism we talk about for this level of indirection? Exactly, segmentation, for example. The other one, base and bound. Okay, so these are three different mechanisms. Exactly, file system having the same structure of that. So what is file system does? File system, the biggest problem of designing file system is lack memory is a mapping problem, but input are different, right? In virtual memory system, let's say you are implementing level of indirection. Let's say you are defining function which performs level of indirection. This function implementation, base table, segmentation, base and bound. And so let's say y equals fx. Then what was the input in virtual address space? What was the input? You can how to understand designing virtual address space. So this level of indirection takes input of what? Mapping input is what? What was the mapping input? Come on. Okay, virtual address space. Okay, what was the return of this level of indirection file system out of virtual memory system? It's called address space. Okay, you can think about that way. So we are dividing several level of indirection. Exactly, file system. What? File name, data, metadata, and map of set of block. So file, so likewise, let's say this is file. So this file, there's some kind of metadata we talk about later. Describe size, ownership, permission, the time creation, etc. Metadata. So, and then there's another file that has different metadata. Okay, we talk about, file system is about, mapping user buffer data into logical location of storage block. So you can map this file data into logical address of storage. Someone say logical block address, LBA. Okay, so map it. So we can actually kind of partition each file according to the block size and store them. And then store the metadata, okay, and name of file. Likewise, this file can be partitioned into different three sector and storing metadata and data. That's what exactly file system does. Can you see the similarity between these two? Can you understand? Okay. So in a design perspective, memory storage system and memory systems are pretty different, pretty similar in this regard, mapping problem. That's key first, right? So again, I want to emphasize that understanding the problem in this design perspective is beneficial because you have some kind of generalized view to understand the design problem, right? So maybe this kind of input and output factors are different, but eventually, memory system and file system also share the same design problem, which is mapping. However, implementing this mapping is completely different because of different performance characteristics, different characteristics of storage devices. So we will discuss some kind of sharing aspect and peculiar to file system, the design aspect peculiar to file system. Okay, so let's summarize. Two systems are pretty analogous. So analogy is virtual memory's abstraction of physical memory. And then there's a level of indirection that I just described virtual address to physical address. Then, so this virtual address is a result of abstraction of physical memory. And file system, there is a concept of file, we already know that, which is abstraction of something. What do you think? Okay, good. Storage. Okay. Which is a set of blocks. Okay, storage. And then level of indirection is file. So this level of indirection is address space. So for example, page and okay, and more than that. So what is the kind of level of indirection mapping here? Again, in file system, file and file to block. Okay, file to a block address. File address to block address. File address. So in a file, you have some kind of addressing within a file. Okay, so AKA, we call this file address in different name. What is it? In POSIX interface, the address within a file. What is it? Offset. Okay. So if you look at file descriptor is identifying a file, and offset is address within a file. So precise way to level of indirection is file, comma, offset, 2 dimension. That are mapping into address of block. That is what exactly file system does in level of indirection. File, comma, offset is mapping into specific block address. Okay, so mapping mechanism, making kind of mapping indirection is called indexing, but they are different from page table or segmentation, talking about later. Okay, the first you have to keep in mind this kind of two analogous designing. So again, recall that, do you remember that many design problems can be solved by introducing another level of indirection, right? Right. Level of indirection is kind of important design term. All right, so that's pretty similarity. So one of beauty of understanding problem this way is that we learn some kind of basics, just mapping. So page table, mapping. You can for page table you actually kind of chunk of file system into kind of specific fixed size chunk, which is called page, and there are table which is can single level multi-level mapping into same granular things. Right, we know that same kind of principle applied to this file mapping in designing level of interaction. That's beauty, right? There are some kind of sharing features. So if you know the one characteristics, you can apply to different domain. Right. So this analogous. So let's kind of talking about the other stuff of file system. So key abstraction or storage is the first abstraction is file. Okay, file is a named collection of information that is recorded on persistent storage. So file actually abstract your storage, right? And each file has metadata, which is called inode. Inode is a metadata. So inode looks like this one. So there's a file type. So file type is the inode is used for file or directory. I'll try talking about directory later. And who is owner in read-write permission, read-write execute permission, and the size of inode. Recall that this is important. Okay, size. So when you are writing a file, let's say this is a file. You are writing a file here. So it's update operation. Then size is not changed. But if you append, then size updated. Okay, so beware. This is kind of important for later in the crash consistency. So this inode has information of size and how many blocks. Okay, and when the file is accessed, when the file is created, about the time statistics and link count. This is about symbolic and hard link. I'll describe later. And this address is actually the index, like a page table, like the feature. So address n is indexing. That is kind of included in this inode metadata. Okay, so each file for management purpose, file system managing metadata. Recall that in the printers, for example, in each memory region can be divided by 4 kilobytes, and there is associated metadata in Pinterest memory, right? What was that? What was that? Page table is table, right? Metadata. Metadata for describing specific 4 kilobyte page chunk. PT, frame, struct page, exactly. Okay. So in operating system, Pinterest has a struct page, which is kind of describing information of struct page. Similarly, each file having a metadata, which is called inode, so analogous to memory, struct page and inode. The struct inode is describing this metadata information for file used for file system. Okay. Okay, these are abstracted. This information does not consider information like SSD and hard disk, right? Okay, so again, these are abstraction on top of the block layer. So if this metadata, including some specifics of SSD and hard disk, you violate level of indirection. Okay, but this information has abstracted. These are kind of gone. So only can see the logical kind of address of storage. And then the logical address can translate the physical address later in the storage section, storage part, device driver, and device. So this abstraction is nothing to do with type of devices, okay, because abstracted. Okay, this is file abstraction. And the second important abstraction is directory. So far, when you are understanding, you are using directory so many times in systems programming and other things. So you can just take it granted, directory. So I can actually hierarchical, naming path name of file, right? But in the beneath, when you learn the file system lecture, you understand the concept of directory. So again, the directory providing the structured way to organizing files. So human are kind of easier to memorize, think something on the classification. So directory actually kind of following the way how human memorize hierarchical information. We can classify. So top level directory provide high level kind of common features of the sub level subdirectories, right? So that's kind of human beings kind of understanding. But under the hood, directory is what? Nothing but file. Directory, okay, directory is kind of file. Okay, but in the file, it can contain any information, right? Any data information, stream of bits put in there. But in directory, no. It has to what? Contain map, a user readable file name to its what? Inode number. Okay, so directory is take an input and output. So what, according to this definition, what is input of directory abstraction? What is the input? Path name. And directory providing some translation, mapping. How to build mapping, I didn't explain, but if you can call this implementation of directory, definition of directory is takes a path name, return what? I don't know. That is definition of directory or level of its abstraction. And you can think about how to path name and map. Okay, so internally, directory has list of array which contain file name to inode number mapping. Okay, and directory is hierarchical. The directory can be placed within other directory. So let's take a look at this, detail. So this is kind of concept, right? We don't know how does it look like, how to represent this hierarchy. In the implementation section in the directory, we will discuss much deeply about this, how directory are organized, how to realize this concept. Get the path name in directory and get the inode. So if you can know inode number, from the inode number, you can locate the file. So that's what actually happens in the file system. So two important abstractions, okay? So file system, components, file contents is sequential byte containing the data, okay? And there's a file attribute, which is not exactly the metadata, but file having some kind of, file having some metadata, which is called file attributes, metadata I9, and which contains this kind of file size and block location using the mapping and ownership and timestamp, etc. in inode. Okay, and to identify file, we are typically using the path name. Okay, using this component, these are interactions. You can have a file name, and then using the directory abstraction, you can get the inode number. From the inode number, you can get the actual inode and then get the file data. So these are translation from file to file metadata. Okay, so this file name is high level interface to application developer, right? From the file name to inode number is row of directory, and from inode number and inode file data is lower of file abstraction. Directory abstraction, it's a hierarchy. Okay, so this is a concept. For this one, there are many other important design issues. So for example, performance, reliability, and scalability. So scalability, we are not talking about scalability, but performance and reliability is important. So we'll take a look. To achieve this design goal, there are many important design issues. So for example, what kind of information it should be kept in the metadata? So if metadata is too big, then persisting metadata to storage device takes some time. So we want to minimize, the size of metadata. Then what is kind of minimal necessary information to keep? Okay, and how to locate metadata from the file name, path name to metadata. Okay, this is directory. Answer is directory, right? And the other one is how to locate the data block from the metadata and offset. Okay, how to locate the data block. We're talking about file indexing. Okay, and how to manage this metadata and data block. So there are two copies, metadata and data. They need to be stored persistent way. So this is kind of talking about crash consistency. Later, okay. How to recover file system after the crash. This is also related to crash consistency. These are important design issues we will explore. So recall that, we are now defining some abstraction, right? File abstraction and directory abstraction, because memory is flat. So memory is nothing but a kind of, flat address space. So virtual address is enough, but storage is hierarchical. So on top of the file abstraction, which is similar to virtual memory abstraction, we need the directory. Okay. So after designing abstraction, what is the next thing to do? Defining API. Okay, like mmap, the virtual address, mmap operation, BRK, that's APIs for memory abstraction, and for file, these are known file APIs. Or on top of file abstraction, open, create, read, write, seek. So file system or file having a different pointers, current pointers, the seek actually kind of changing the offset within a file, and close. And importantly, fsync. Okay, so for the fsync operation, we will discuss much later. But what we are not kind of let's say why this new API is required. For example, why fsync API is required. This is kind of pretty different from memory system. What is the semantic of fsync? Why this fsync is required? For example, these APIs. What do you think? So sync keys, the name. I really like this. Okay, I really like this name of sync. Sync, synchronizing between what? Synchronizing between what? Cache and actual storage. So later, file contents are cached in memory in DRAM. And later in the storage, logical. These are loading into memory DRAM. And then when you are write data, does your modification apply to here or here? Cache or storage? Cache or storage? Cache. So here are updated version. At this point, this one is different. So the semantic of fsync is synchronizing these two devices with the same content. So this is called fsync. Okay. So fsync operation is the file system API, whether the modification only made in the DRAM file. So there's two versions, DRAM version and storage version. Two files are synchronized. Contents are going to identical. Contents. Okay, so that's fsync. We will deeply discuss the semantic of fsync, how to implement fsync. So fsync contains many details, but that's a high-level semantic as a design perspective. One can make this content identical. And rename. So the file name can be changed. Rename operation intuitive. Unlike I want to delete file the path name, delete file the path name specified. Instead, providing some kind of how can I say, the information. So who is the owner, what's permission, this query. And link and symlink I will discuss later. And mount and unmount also talk about later. These two are, the API semantic we discuss. So these are file system APIs. Let's talk about first thing. So directory and path name translation semantic. Okay, so path name. These are a bit including some kind of details. So please understand, please kind of focus what I'm talking about. So you are trying to open. Okay, so this path name, this path including 3 directory, root directory, first, second, home directory, third is home/tom. Okay, and then this is actually file. Okay, so after open working directory, what was the eventual outcome in the figure? Directory, you can traverse the directory. So after traverse the directory, what are final outcome you want to get in the file system? Siwan, I'll get back to your question soon. So what is directory? Input path name. Output what? What is output in directory? inode number. This one. So eventually what you want to get is this inode number of foo.txt. Okay, so to do that, you have to work in this directory. First, open directory, root directory. So if you are opening the root directory, again, I say that directory is a file, right? So if you are trying to open the root directory, directory having this file system content. Okay, so root directory you can get the inode of root. Okay, then read file contents of this root inode. Then you can get this content. Okay. For this one, the location of inode is well known. So root directory, the inode location is always fixed. So read this inode. From the inode, you can get the file contents. The file contents, nothing but this array, file name and inode. Okay, so then we know the home directory inode is 185. Then what is it? Then read inode of 108. Okay, in the inode there is a pointer. There is a pointer to point in the contents of file. Search, and until you find the next directory, tom, which has inode 830. Okay, read inode and got the contents of this one. Same thing, read inode, get the contents of this one. So that is exactly what happens in the open. So open involve directory walking, hierarchical directory walking. The directory walking is a get inode number, read content, and finding next path name, and searching this directory blocks, and finding the next directory's inode number and read inode number iteratively until you get to this .txt. So that is how directory works. Obviously, the permission checks happens in each step. Okay, so that is path name translation, and this directory operation involved for this path translation. Okay, so file systems spends lots of time walking down this directory content. So operating system typically caching contents of this directory to enhance performance. Path translation. This is design of path translation. to implementing directory, you have to first how to translate things in path name as path name. So these are kind of key features to implement directory concept abstraction. Okay. Second thing, now so after API, I enumerate important designs kind of this parallel way. So the thing is that first thing is that path name. The other thing is mount concept, how the mount concept is designed, and the second thing is link concept. The link idea is API is how it does link API is implemented, and the other one is persistent operation, async operations implemented in design, and then crash consistent semantic and moving to implementation. Okay, so these are structure to be aware of that. So first thing was path name translation. The next thing is about mount. The mount is a file system unique operation where a file system has to be mounted before it can available to process on system. So memory operating system just kind of detect and building virtual address abstraction, but in the file system there are special API that expose part of your disk, hard disk, or storage device can expose to application. First of all, why this concept of mounting is important? Required? Why do you think? Think about that. Why mount operation is required? For example, in Windows, we have different layers. 네, 운영진들 수업 중입니다. 죄송합니다. To provide protection. Good. Good. Yes, but actual region is different. Think about that. Unlike memory, why file system designers invent this concept of mount? Scalability. What? Devices are detachable. Okay. Devices are attached detachable, right? Why? First of all, in DRAM, different type. First of all, we need to handle different type of device. So some device represent hard disk, some device SSD. They are different. There are multiple. So unlike DRAM, in DRAM, if we can plug more DRAM units, does kind of operating system distinguish two different DRAM? I will explain to you later about mount operation. No, right? But in device, they are different. So the concept of mounting is that, this directory hierarchy, this directory has this kind of hierarchy: root, users, and Sue, Jane. And I want to use this part SSD. I want to use this part HDD. That's possible, right? That's kind of, sometimes Jane is kind of not frequent user and they pay some small amount of money. So I want to give this home directory as cheap hard disk. I want to use this Sue, which is important, and I want to apply for SSD. So this directory providing this hierarchical information, and I want to using different storage for different hierarchy. Okay, so that's kind of goal, and mount actually allow this kind of concept. So when you are mounting file system, this is a directory for this root directory amount. Root directory is mounted to SSD, and /users/Jane is mounted to HDD. Okay, so this namespace from now on, the subdirectory are using HDD, so we can provide different mount point. So each namespace provided by directory, you can attach different type of devices. Okay, for convenience, we are trying usually use entire directory as single device, but that's only the case where you only want one homogeneous device. But if you have servers having multiple devices, the correct way, we have to consider the case where each directory and users having a different type of devices. So that for that purpose, mount operation happens. Mount takes what? There's some kind of flag, some kind of information, but source. Okay, and character. So this actually takes up path name. Target. Sorry, source. I'm not sure what is for source, but target is actually this mounting target of this users home slash user state. Is take this control on, and source is type of device made probably like DV / HDD, DV / SSD is source of device, and target is the namespace target path name, and you can actually apply the path using this device specified in the source. And unlike unmount, clearly just kind of provide, I don't want to using this path name, so this path name is unmounted, detached. So can you understand what is mounting? So I didn't before describe the mounting. I just kind of briefly explain the use cases and why mounting is required. Any questions about mounting? Okay, so in Unix, to an existing empty directory, and different file system can be mounted in the same tree. So same tree here. For SSD, you are using some file system called FTFS. For HD, you can use ext4. So different file system can support a different file tree. This form of large and single directory tree. To Unix, on existing empty directory. What is it? We call what is destination? In Windows only providing this thing, but in Unix, which one? We call mount point. Okay, mount point is specified this home / J. Okay, that is mount design. Okay, we don't talk about how to implement mount. This is concept. Okay, a different file system having different implementation. That's basic design of mount. And the other important design thing is hard and symbolic link. Sometimes when you are implementing a file system, you want to copy. So hard and symbolic link is about pointing. So hard link is the command via ln. So old file and new file. So this is concept of hard link. Both path names. What path names? Let's say current home directory / home. What path names? Home / ol old text / home new txt, but same id. This is concept. I want to use these two files as the same inode number. So same inode, okay, having pointing both this old and new file, meaning that new and old file are identical, okay, identical, so that they share the same inode number. So from this point, we cannot tell which one is original. Who is the owner? No, both are shared inode. So inode has two number of holding. Where's link count? Okay. Now, can you please describe how mounting works a bit more? Mount works a bit more. Okay. Sure. I will get back to your question soon after explaining this link. Say someone ask the caching questions and the mount questions. I will get back to you soon. Okay, so these are hard link. And delete. Delete is done by this unlink operation given by path name. Delete is decrease link count. So if I want to unlink this one and this count, so meaning that this original the home/old txt still survives. I know this removed file is completely deleted only when the link count becomes 0. Okay. So because I know they are shared, hard link does not work across different file systems. So for example, in this is namespace, this is directory. I want to use this directory for SSD. I want to use this file HDD across because they are using different file systems. Hard link does not support across different mount points. Okay, so this is a comment. LSI is printing inode number, old.txt and new.txt. So old.txt and new.txt having same inode number. All right. So the next thing is about a symbolic link, but someone asked about questions about mount. So Halia, could you sorry. So the mount operation I will explain later. So is there any before moving to symbolic link, is there any questions about mount? So confusing. So mount is operation like this one. So for example, you have path AWN and a.txt. So this directory hierarchy explain yjkwn and a.txt. So these are namespace by directory. And root directory can be mounted by SSD. And without any operation, the mount means that this the hierarchy, this hierarchy below the root directory, we aren't using SSD. So mount, you can see the mount operation is attach device to specific directory location. Okay. And then, so SSD is formatted, for example, to FTFS. FTFS is nothing but a file name, a file system name. So FTFS used for presenting root directory. Okay, and home. I want to this part I want using this FTFSD, but this one I want to using HDD. HDD is formatted to ext4, for example, Linux. So I want to mount ext4 file system to home. Then from the subdirectory below the home, we are start using the ext4 file system running on HDD. That is concept of mount. So mount is how to attaching the file system to specific directory location. Make sense? Okay. So okay, good. There's one thing I want to explain about mount operation. Okay. Yeah, I think I forgot that, but that's enough to explain that. Okay. Because of that, in directory, you can create a link. For example, I want to make a link. So Sue and Sue actually pointing to this original location. This is done by link. So hard link and soft link, symbolic link. So we talk about hard link. The second link is symbolic or soft link. So the command including this -s option. So this new file contains a reference to another file or directory. Okay, so symbolic link, you can think about the shortcut. Okay, so let's say these are files, and let's say you create symbolic link of file 2, which are linked to file. So if you can vi file, vi file 2, they both open the same file. Okay, because they are linked. However, symbolic link are different. In symbolic link, did I prepare? No, I think. In symbolic link, unlike hard link, symbolic link creating new inode for file 2. Hard link, in hard link, this file and this file having the same. Where is it? Same item number, but in symbolic link, you create different file. So, which implies if you are creating a symbolic link file 2 and you are delete the file on link, does link, how do you handle with this link? Does the file system also delete the file 2? Yes or no? If in symbolic link, there's a kind of the symbolic link is not different inode. So if original file is deleted, does operating system delete file 2 either or not? What do you think? What do you think? No. Why? Because it has independent inode. So going to your laptop in Linux and then explain, do this practice, whether hard link, what happened? In symbolic link, what happened? In symbolic link, it doesn't do it. Symbolic link is subject to dangling reference. So you can create a file and create a symbolic link, and you can check the contents of file 2. File 1 was hello, file 2 is also hello. So in symbolic link implementation, in symbolic link file 2, it opened inode file 2. This inode are pointing to file 1. Okay, so that the contents of file and file 2 are identical. And then you delete the file, unlink file, and you can open the file. But so no such a file directory because cat and file 2 and file 2 was pointing to file but cannot open the file, so return this no such a file directory error, which is dangling reference. It's possible in symbolic link. So unlike hard link, symbolic link having a different inode, so deleting one file, and but the link location still inode survives and having point to the old location, so that this dangling reference problem happens in symbolic link. But despite of that, why people using symbolic link? For that one, is because symbolic link does not make a cycle for this directory. The hard link providing cycle. So, for example, in namespace hierarchy, if you make hard link, which creating a cycle. So this is not the actual inode. This location pointing to here. So when you're working on directory, going here, making a cycle. Cycle is sometimes pretty bad when you are kind of searching large number of directories. The hard link is not how can I say desirable. So people using the symbolic link, which does not create a cycle. Let's not talk about that. But that's the two different link operations. So people much prefer to using symbolic link. Okay, used to. Okay, so then the next concept is persistence. For performance, it is natural to implement file system leveraging DRAM. So disk, the contents first reading into cache. The contents of this first reading into cache. Okay, the file system buffers this write operation. Read operation also buffers, and write operation also buffers into memory. So if you are first trying to write a block, what file system first to do is loading. So first try read block into cache called page cache. So write operation involve read operation and update it. Okay, so that's possible. So file system first buffers write, reading from disk, and update operation. Okay, so this definitely the purpose of this buffering is improving the performance. And the contents that retain the the memory is 30 seconds. In Linux, periodically after every 30 seconds, it's written back to storage device. But if application want to synchronize at some point, a specific point, it requires fsync system call, which flush all these dirty modified data to storage and tell the disk to flush the write cache to media. Okay. And also when writing back to disk, flush metadata information associated file too. For example, file is increased, the metadata length is increased, the metadata and file data both has to be persisted. The fsync guarantee both metadata and file data. Okay, and there's a different API fdata sync. It does not flush metadata. For improving performance, fdata sync is omitting the flush of metadata. But fsync is a more general API using synchronized contents between cache and storage devices. These are API. So open file, and then we can write the data in buffer. So this is first buffer size to this file. And so the first file system have to read this buffer content and then put in the cache and update data and write down fsync and close. There are thorough issues whether why file system has to be loading data. So for example, let's say your buffer is 128 bytes. This is about implementation, but let's talk about that. So 108 bytes, and your file system block data is 4 kilobytes. So to update it, you have to read into memory and modify 128 byte content and return back to file system. So because IO granularity is 4 kilobytes, if you sub IO granularity updates, have file system read on contents and update only portion that's of 128 bytes and write back. So read required. When your buffer is 4 kilobyte, file system optimized without reading and just kind of write back the 4 kilobyte data, but that's kind of an optimization point. But if your buffer is smaller than 4 kilobyte, then read and modify 128 bytes and write back. That's common implementation. Okay, so that's ensuring the persistence. So persistence is nothing but synchronizing state of DRAM and storage. So states, I'm talking about two, data and metadata. So that's concept of persistent. Okay. Okay, so these are that. And then the next thing, let's talk about this one in implementation next time. So the remaining part, the final remaining part is sharing consistency. So two processes may open a file. So files can be shared. That's a possible case. And write up the semantic, how to implement it. No, I'm talking about design, design. Unix design, when you open a file and write to the open file, immediately visible to others that have the file open at the same time. Okay, that is Unix semantic. AFS is Andrew file system, which is kind of distributed file system, but it has different semantic. The updates to open a file are not visible immediately. When file is closed, the changes are made to file are visible to the other users. This is called NUFS session semantic. Okay, so in both Unix is more common. So we just kind of talking about implementation of Unix semantics. And the other one is immutable, unchangeable shared file semantics. The file is shared, but read only. Okay, so only files declared shared by its creator cannot be modified to other users. But these are not popular. So Unix semantics is most popular semantics, and also Linux using this Unix semantics. So key thing is that updates immediately visible. Okay. How to ensure that updates are immediately visible to other users? We learn memory session, virtual memory abstraction. So this is a kind of design idea. And what is your implementation strategy to follow this semantic? What do you want to do? Any idea? In memory. So recall what we learned in the memory. What kind of feature? Cache and shared cache. And plus what? Cache is fine. Cache is just kind of putting user level file into cache. Then plus what more? User level file contents into DRAM, and one more kind of operation is required. What? Shared page. Good. These two allows this immediately visible semantic. Here is the example. So these are file, and here's the DRAM, and here's your process. Process 2. Okay, the file are loading into here DRAM. Let's say this is cache managed by who? Managed by who? What do you think? I mean, guess. No, you can guess it. Cache is managed by user or kernel. What do you think? Give some sense, right? Okay, yeah, right. So without explaining some detail, you guys now you can understand. Cache is kind of allow shared mapping. So cache content has to be managed by kernel, and process virtual address space that maps same. So if you can modify one content shell file, and this modification are made by this shared cache, and this modification immediately visible to other file, other virtual memory. So because memory is shared memory, page table pointing to same physical DRAM. So that is Unix semantic of shared file. So caching data into DRAM, the kernel managed cache, and let application having a shared mapping. So that's using this mechanism, we can implement this Unix semantic of sharing. Right, so that's all. And next time this is summary of design. So that's kind of necessary design. So we kind of talking about important design feature, design concepts, and mapping problem, similarity with memory and APIs, and different kind of these different semantics and operation in design. And let's talk about implementation. So how to implement these concepts using file system. Okay. All right, so that's all for today. If you have any questions, feel free to ask. Let's talk about last into the implementation section. Let's do implementation section in this Wednesday. I think one question about the caching, the synchronization always happens from the memory to storage side. That was your question, right, John? Correct? Yes. Yes. The synchronization is kind of always the data update modification always made to buffer, not the storage device. So synchronization always having made it to DRAM up hierarchy of memory and low hierarchy of memory. So DRAM to storage, that's common. What is the meaning of attaching specific file system to directory? So here's the example. Let's say you have two storage. So this is a logical space. and you have this namespace hierarchy. I want to use this one SSD, this part as hard disk. So if you can create a directory and other files, they are stored in the SSD. If you can create the file or write on data, they are going to hard disk. That is the meaning of attaching specific file system to directory. So here's the case. Let's say if you can write a file one and file two. Write file one goes to F2FS goes to SSD. Write file two goes to ext4, it goes to HDD. So, in the directory, because know that this file creation where to go to directory. So if you can write the data and kernel kind of deviate this file operation. So that's kind of what happens in attaching. Does it make sense, Johan? Okay. Can you re-explain ensuring the persistent page in 617? Persistence. Persistence is that when you are updating the data and then DRAM, you have to up-to-date copy. Up-to-date copy. So if you can modify something, this has to be written back to hard disk. So this persistent operation ensures that this modification is made to disk, but at the same time, recall that you have inode. So this inode and data has to be persisted together. For this detail, we will deeply discuss in the crash consistency section. So there are two ways to persist. First, Linux periodic automatically write data into storage device at every 30 seconds. Or application explicitly call this fsync, then this metadata and data are synchronized. There's another API called fdatasync, which does not persist metadata, but persist data into storage devices. So this is fsync and fdatasync working differently. Does it make sense? That's kind of a concept of persistence operation. Okay, can you explain again why link operation needed? Also, how are files with the same inode number distinguished done by Harlan? Sangmin, good question, but to precisely understand, explain your question, I need to explain some indexing design, indexing concept. So what is the meaning of sharing inode? Why they can go to the same location? So here's kind of way you can understand. You can go to directory working. So directory working, say ln old txt, or link new txt. So old, then directory returns inode, right? And directory walk new returns same inode number. So directory contents having a same inode number. So that's the easiest way to understand hard link. In symbolic link, they are different. So directory block, old txt, new txt, they having inode number, they are identical. So when you create a hard link means that you have to adding the directory block with the same inode number. Does it make sense? Okay, good. Right. So any other questions for system? Okay. Thank you. So let's keep talking about file system in this Wednesday. All right. Bye.